The Cross-CPP project gives cross-sectorial industries access to a huge amount of sensor data coming from high-volume products such as vehicles or smart buildings. The new information sources create new value, improving existing services and fostering creation of new cross-sectorial ones. Sensors in cars, buildings, and other cyber-physical products, or CPPs, are permanently on and produce invaluable data. Companies, such as Volkswagen with their cars or Siemens with smart buildings, benefit from the new opportunities and deliver better services for their customers. However, there is currently no brand-independent solution in place that would define a unified form of access to such data. It means that every service provider needs to negotiate many contracts and interfaces to process data shared by its owners. The project overcomes these issues by defining a unique ecosystem integrating data streams coming from various cyber-physical systems, especially in the automotive and smart building sectors. It pays particular attention to intersectorial data and services. In general, the Cross-CPP ecosystem can be separated into 3 pillars. They will be described in the next slides. And it is relevant to various types of stakeholders, especially CPP manufacturers and service providers that can benefit from the cross-sectorial data. The left pillar corresponds to data providers, CPP manufacturers. It comprises data harvesting and making CPP data from various industrial sectors available, transferring brand-specific data streams into the common CPP data model. The middle pillar consists of the Cross-CPP cloud storage and big data marketplace. The CPP cloud storage enables controlled access to CPP data from different sources. The CPP Big Data Marketplace offers support to service providers in the form of easy access and detection of needed data. It also includes an analytics toolbox enabling service providers to process and analyze CPP data streams in a flexible and efficient way. The right pillar is relevant for data customers. Service providers can use available CPP data from various products to create new services and to improve existing ones. The project brings various innovations. 3 key innovative aspects include: definition of a standardized way to collect and provide data with the focus on privacy and security. Creation of a one-stop shop for the data and its analytics which simplifies the use of the data by service providers. Demonstration of many advantages of the developer ecosystem in the form of innovative cross-sectorial services by Volkswagen, Siemens, and Medialogix. Members of the user interest group will be able to validate the mechanisms to have full control over their valuable data as owners of relevant CPP data and the ease of defining new services employing the data. Okay, a brief summary of the data harvesting and company backend functionality. As already mentioned, the main role of the CPP data harvesting is to acquire the data from a proprietary CPP data source and send them to CPP company backend. To ensure that the data harvesting process is in consent with end-user needs, a data acquisition configuration is downloaded from the CPP company backend and deployed in the CPP data logger. The company backend represents the central data access point to the CPPs for thousands to millions of CPPs of a brand. It is based on a proprietary brand-specific solution, interpreting and transforming proprietary manufacturer-specific CPP data into physical information in reference to agreed owner permissions. Furthermore, the information is validated and can be masked to enforce privacy. Data providers, such as VW or Siemens, have contracts specifying under which rules data owners, individual end users or business CPP owners, such as fleet operators, agree with the use of their data for particular purposes via the Cross-CPP marketplace. Each data provider is then responsible for data harvesting, pre-processing the collected information in the company backend system, and sending it to the data marketplace. From a general point of view, the company backend data processing usually involves data validation, cleansing, normalization, aggregation, and transformation into the unified CIDM format. Volkswagen and Siemens implemented their respective backends for demonstrators in the Cross-CPP project. Using existing data harvesting components, they were able to pre-process the data for their customers' CPP data owners, transform them into the CIDM form and provide the results through the Cross-CPP data marketplace. The Cross-CPP Common Industrial Data Model, or CIDM, harmonizes proprietary data and provides means of transforming it to a generally usable form. The Common Industrial Data Model was defined to simplify the data exchange between two key stakeholder groups: CPP data owners and providers of services employing the data. The design of the data model was based on a detailed analysis of the requirements of both the groups. They provided feedback in several iterations and verified the applicability of the final specification of the data model. Key requirements on the CIDM include its scalability, brand independence, and openness, as well as its ability to cope with the high diversity of IoT data, the support of various signal and measurement types, and the focus on data ownership transparency. Key concepts of the model include signals, channels, and data packages. Signals describe the type of physical phenomena and chemical quantities of CPP, including the name of the signal, the format, and unit. Data from CPPs needs to be pre-processed and aggregated conforming a measurement channel that includes one or more signals to be aggregated, the aggregation type, time series, histograms, etc., and the configuration of the aggregation. Data packages provide the actual data coming from a CPP, aggregated according to a measurement channel selected. CIDM signals usually correspond to sensor measurements or status information. The data format enables defining various signal types and other characteristics of the signals. To cope with potentially enormous amounts of data and, also, to reflect strict data privacy settings, the data model defines a data aggregation and downsampling level of measurement channels. For example, the data can be sent as aggregated time series, a histogram, or a geo-based histogram channel. A collection of the data corresponding to one measurement channel and relevant metadata is then referred to as a data package. Data packages are the basic blocks manipulated by the Cross-CPP data marketplace. They are stored and indexed and can be retrieved by means of the defined API functions. The physical data model is implemented in JSON. Signals and measurement channels corresponding to the vehicle and smart building data were defined in the Cross-CPP projects. OEMs from other sectors can easily extend the model by defining plugins for their specific areas. The following screencasts demonstrate the marketplace functionality relevant to data providers. Data providers can review the collected data in the marketplace. They log in with the credentials given by the data market operator and can interact with the system. The Data Vault subcomponent summarizes key statistics on the data collected and it enables accessing other relevant actions. When thinking about new data that could be provided, data owners can browse the data catalog and examine the signals that have been already defined and are available in the data marketplace. They can have a look at catalog details associated with signal definitions, and consider whether a particular signal is relevant to their needs. The signal catalog can be also filtered based on various criteria such as the cyber-physical product type that narrows down the list to signal relevant to a particular profile. Data providers can also inspect the list of the data packages they sent to the marketplace. They can examine global statistics and check metadata on all the provided packages. The data package detail then gives specific information on the reported measurements, such as its exact location or visualization of the data. The Cross-CPP project gives cyber-physical product users, individual or corporate data owners, a full control on the use of their data. They can choose whether or not to share the data with third parties and have contractual guarantees that the data will be only used in the way to which they explicitly provided their consent. A key part of the contract and consent management takes place at the link between the company backend and data owners. The data provider is responsible for ensuring that the data collection process is in consent with user intentions. The company backend has to handle the consent of each particular data owner. To guarantee the transparency of the data usage, the system provides mechanisms for the data owners to be always aware of what entity is using which data for what purpose, even for the usage of anonymized data by a service provider. The privacy preservation considerations are embodied into operational interactions between the data owner and respective shareholders of the overall Cross-CPP ecosystem and are part of the project solution. Even if a data owner agreed to provide his or her data through the data marketplace, the data use for a particular purpose is determined by accepting a data request offer defined by a service provider. Data providers can examine details of particular offers and the way the data would be provided and decide whether they correspond to the intended data sharing. The screencast shows how the data providers can accept data access offers created by service providers and how they can terminate formerly accepted contracts. The data wallet contains the list of all the published offers. The user can review the channels that are requested and other parameters of the proposed offer. They can also consider the intended use of the data. Finally, the user decides whether to accept a particular offer or not. The data wallet also enables inspecting the list of previously accepted offers. If the user decides that the data should not be provided to a particular service anymore, he or she can terminate the data provision contract from the list as well. The contract remains in the list of previously accepted offers with an indication of the termination date. The security objectives of the Cross-CPP project arise from marketplace challenges, including support for dynamically changing confidentiality, privacy, and intellectual property constraints, as well as ethical requirements, which we refer to collectively as security constraints. There is a need to assure optimal management of security constraints depending upon the actual context under which data streams are used or generated. This demands that services can be adapted to the current needs of the user according to the security constraints and conditions relevant to the current context of the user, the device, or client application. A definitive new requirement for Cross-CPP is context sensitivity security with the ability to adapt the policy at runtime according to the context. Here we see the implementation of the context-sensitive security design paradigm in the CPP Big Data Marketplace. At the heart of context-sensitive security is the lightweight next-generation access control components developed by the Open Group. A declarative policy language based on the NGAC industry standard policy framework is used to express an access control policy for data, devices, users, and other resources within the CPP Big Data Marketplace. A policy tool is used to develop and test security policies expressed in the language. One or more policies may be loaded into the policy server and combined to elaborate complex security policies. Policy enforcement points along the resource access path mediate access to protected resources by client applications. Upon receiving a request from a client application, the policy enforcement point asks the policy server for a policy decision according to the current security policies. The server replies with a grant or deny response and the policy enforcement point acts accordingly on the client request. A definitive new requirement for Cross-CPP security is the ability to adapt the policy at runtime according to the context. This is accomplished through an interface with the Cross-CPP context monitoring and extraction module that provides a context mapping for policy rules and the ability to modify policies based on context changes. To meet the marketplace challenges, innovative context-sensitive security components allow the definition and enforcement of policies for data access. These policies can range from global platform-level policies, to policies restricting access to particular items of data in a dynamic way. The key security innovations include fine-grained end-to-end security policies capable of protecting data at multiple levels in a distributed system. Multiple security policies and composed security policies to factor complex policies into portions that are easier to administer. Security policies conditioned on dynamic context. A policy is interpreted according to context variable values. Event response language for dynamic policy change predefines policy changes to occur based on context change notifications. Scalable for big data and many clients, permitting policy data objects and users to be added or removed dynamically.